But so what I will talk about today is that we also do quite a bit of research, and research is applied research. So a lot of industry company collaborations, of innovative projects, of how actually the current research results can be combined with really the real world business, so to say, right? And so this is a project that we have together with Securosys, and I will tell you a little bit about that. Okay. And we heard actually today already quite a lot about post-quantum cryptography. I was quite surprised, but it was mentioned in almost every talk, I think. Yes, and we heard that Securosys HSM is now post-quantum ready. Maybe you also heard some headlines in the past few months that, well, messaging apps which have become quantum safe, or browsers, also a few of the infrastructure in internet in general, several libraries which now include quantum safe, or even were specifically made for post-quantum cryptography that deal with that. And for example, Cloudflare has this graph showing how big is the adoption of post-quantum cryptography in the internet. And you see that we're here at about 16.7% currently of post-quantum encrypted connections. And what you see here, the increase, this slight increase here, oh yeah, I have it. And the larger increase there, that's largely because of the Chrome browser that adopted post-quantum encryption as a standard. And this actually went quite smoothly. It did show some issues. For example, it turned out that AWS had in their library some limitations of how many signature algorithms you can actually have. And that was started to be an issue. I mean, issue totally unrelated as such to post-quantum cryptography. But so this could be solved. And in general, this was all quite smooth. Okay, so yeah, why are we even still talking about it? Of course, the truth is a little bit more subtle. So you hear now a few applications that do include post-quantum cryptography. But if you check here, it's all post-quantum encryption adoption. So all of these applications that have included post-quantum cryptography, they do this on the key exchange with the new algorithms. And I will go a little bit more in detail on that. So for example, these connections do not include the post-quantum authentication. And it's really there, it's a little bit more difficult, okay? Yes. So yeah, so the encryption actually works smoothly, and I have also prepared a demo for you, which is over there on our table. We have made a project where we created a matrix server, and the connection is with a post-quantum key exchange, and so you can do video chat quantum safe, okay? Really, the main point was to show that you don't see that there is anything different and that this just works smoothly. But you can check it out there. Even you can go with your own computer and connect to that thing. Yes. So what we want to do, or what the project that I will talk about, is about this project with Securosys. And it is supported by the Swiss innovation agency InnoSwiss. And we want to study together with Securosys, what does it mean from a functional point of view, this change to post-quantum cryptography. Does this have any implications on how things work? Does it cause additional delays? Or does it, for example, cause more of the connections to not get through? Or what implications are there? Okay. And we do this at the example of TLS connections. And that's what we want to see. Like, if we do a post-quantum key exchange in TLS, is it slower? Does it abort more often? And we want to look at this in a realistic scenario. So we look at it with networks with losses or delays. And most importantly, contrary to most of the examples we have seen before, we also include post-quantum authentication. Okay, that's what I will talk about for the next, like, maybe 10 minutes or 15 minutes. I will give you a little bit of context of post-quantum. Maybe you've already heard some of it today. Where does this fit in? I will show more precisely what we mean by there is a difference between key exchange and authentication. Why does it even matter? And then I will show you some first results of the measurements that we did. Okay, well, we heard already a lot today about post-quantum, and maybe some of these things you have already seen, but of course we wouldn't be talking about post-quantum if it wasn't for quantum, okay? So quantum computers were proposed somewhere in the 80s from the theory side, but really the last few years from the technological side, they have increased a lot, and there was quite a lot of development. Nevertheless, I mean, they're still small, and large quantum computers are still a thing for the future, okay? However, we are really interested in quantum computers because we know that they are a threat for public key cryptography, which was found by Shor's algorithm in 1994. Okay. And even though the quantum computers are still a thing from the future, or the large-scale fault-tolerant quantum computers are still something that is to be developed and is not there yet, the people are fearing this development because one can record today a conversation and then use the quantum computer later on to decrypt what was used to encrypt the things today. So that's commonly known as harvest now, decrypt later attack. And it essentially means that it's not sufficient to wait for a quantum computer to exist to do anything. But one has to act really before. And that's why NIST has started a standardization effort in 2016 to a call to propose algorithms which are designed to withstand attacks by quantum computers. And most of the proposals that were done, however, based on cryptography that is from the 80s, 90s, some of it before even Shor's algorithm. So even though we know it as post-quantum nowadays, the basis of that was already known before. And that's why also some of the standardization has been possible quite fast. So Marcel mentioned the stateful hash-based signatures, which were already are around since a while. But really, many people have been waiting for the results of this NIST standardization effort. And in 2022, they published which algorithms they want to standardize as part of this call. So 1 for key agreement and 3 for signatures. And this has also led to a few government bodies making some statement about post-quantum. Most of it so far is not really yet that you have to change to this and that and this and that, but rather a kind of a looking forward that it will happen. And just last month, the first 3 standards have come out from these selected algorithms, and the last one I think is still to be expected this year. Okay, so quite a lot happening now. At the same time, while these standards come out, so NIST has also issued another call to propose additional algorithms, mainly with the background that they would not like to put all the eggs in one basket and have algorithms which base on different mathematical problems additionally. So there is further calls for key agreement and also signature algorithms, which will come only probably in a couple of years. Okay. So it's still, the research is also continuing. There is still new proposals. Okay, let's get a little bit in the technical details. So I said a little already that the post-quantum cryptography is relevant in the context of public key cryptography. And for sure, the probably most famous application of public key cryptography is TLS. And that's also what the project is about with Securosys. So I will give a little bit more detail of what this means and where does it exactly come in, okay? So the goal of TLS, so TLS has these 2 phases, handshake and application data that is exchanged. And the goal of TLS handshake is to agree on a shared secret key that the client and the server can use to encrypt and authenticate the data that they're exchanging, the actual payload. Okay. Now, once they have agreed on a shared secret key, they will use so-called symmetric cryptography to both encrypt and authenticate. So they will use algorithms such as AES or hash functions to do this. And this part is not considered broken by a quantum computer. Okay. We can argue a little bit about key sizes, as Marcel has introduced, but the algorithms are not considered bad. Okay. So these are considered fine, these algorithms. And so that part we are not really worrying about too much, okay? So the real issue from quantum computing comes in here at the top, which is the protocol that actually is made to agree on these shared secret keys. And here, public key cryptography actually comes in two ways, okay? And the first is that the two sides agree on a key, and they have this key agreement protocol. And traditionally, this would use algorithms such as Diffie-Hellman or something like that. It's all done on a very conceptual level, the image, okay? Just so you know. And in the course of this key agreement protocol, the two sides will create pairs of public key private keys and will send around these public keys. And in the end, they will agree on a shared secret key. Okay. And this public key cryptography here, it is vulnerable to attacks by quantum computers, so by Shor's algorithm. And the problem is it's not only vulnerable to attacks by quantum computers, but also if you record the communication that is done here, you can use the quantum computer at any later point in time to break this cryptography and to find this shared secret key here in the end. And then this will allow you to break the security of all the communication. So this is exactly this harvest now, decrypt later problem. And that's why the moving this key agreement part to post-quantum is considered quite urgent or comparatively urgent in TLS, okay? Now, on the good side, this public key cryptography, it's really only used during the actual handshake. So these public key private key pairs, they are created during the protocol. In the end, they are trashed, okay? So this cryptography is part of the software there, and the keys are only used temporarily. So often we can move to post-quantum cryptography here by a software update, essentially. We don't need to change too many things around. Not saying in all cases that's easy, but that is essentially what has happened with the browser and with the chat messages that we saw before. So Chrome is now using post-quantum cryptography by default. So chances are that you might be using post-quantum cryptography for key agreement with your browser, and you didn't even notice that your browser got updated or that you might be using that, okay? Now, there is really a second part of public key cryptography in TLS, and that is for authentication. So the two sides don't just want to agree on a shared key. Of course, they also want to make sure that they agreed on the key with the correct person or server or whatever it is. And this is done with the second part of public key cryptography that is used in TLS. So in case of one-sided TLS, the server will have a certificate with a public key. And to authenticate, so they will send the certificate and then they will sign the transcript of the communication using the private key of that certificate and send this to the other side. Okay. Traditionally, this would be done using RSA or digital signature algorithm or something like that. And the important thing is this is a different key pair than the one that we have used before. Okay. So this authentication, it's also vulnerable to attacks by quantum computers. But if I can break this authentication, I cannot use this later on to find this shared secret key here, okay? So if I can break this authentication, I can do a man-in-the-middle attack. And that's what we want to avoid, exactly. But this man-in-the-middle attack would need to happen while I do this TLS handshake, okay? So moving here to post-quantum signatures, it's maybe not quite as urgent as the key agreement, but it is also even more difficult because, first of all, we have the certificates. The certificates are not just used during the protocol, but they are more long-term, right? They have to be emitted by a certificate authority. So these certificates would have to be changed if I want to do post-quantum signatures and authentication to include keys that are for a post-quantum algorithm. And even worse, it's not just this one certificate. The certificate is also signed again and is also signed again by a certificate authority, right? So I have a whole certificate chain. So in the end, I would also need to change actually the signatures of this complete certificate chain to really be fully quantum secure. And many of the signatures that are done with, especially on the certificate authorities, they will involve actual infrastructure such as hardware security modules, which also need to be able to do that. Okay, so this post-quantum signatures authentication maybe not quite as pressing, but it involves a lot more changes. And also because we do have these whole certificate chains and actually further additional signatures which happen in the TLS connection, we don't just have one signature, we usually have several signatures. So if we have performance impact of the post-quantum algorithm here, this can multiply because we actually use them several times. Yes. So careful, I said the signature and authentication in TLS, it's maybe not quite as pressing as the key agreement. This is really something that is only valid for the TLS connections. If you have signatures in other contexts, like signing contracts, this might be totally different. So in general, as long as you accept contracts with that type of algorithm that is maybe not quantum secure, you might have a problem. You might have a problem for the legal history, for example. So really how pressing, how urgent, how difficult it is, it depends very much on the precise use case. Okay. Okay. So that's what we are seeing now. This is really what has happened now that key exchange have changed in a lot of applications to quantum safe. And to be precise, all of them, of course, have not changed just to post-quantum cryptography, but they have changed to a hybrid solution such that they are safe if either hybrid or the current algorithms are, if either the post-quantum or the current algorithms are secure. Okay. On the other hand, for the signatures and authentication, we have not seen many applications changing this yet because it will need to have CAs which support emitting certificates. And we're expecting this to pick up now, but it's not really used so much in applications yet with the post-quantum authentication and signatures. So yeah, so that's what we want to study together with Securosys, or what we are studying together with Securosys. So what is the impact on the TLS connection if we now don't just do post-quantum key exchange, but also post-quantum signatures? And for this, we have set up some experimental framework which measures how do these TLS handshakes behave in this post-quantum setup. And we have some preliminary results, which I'm happy to show you here. So actually, if we look at the different algorithms, these are the algorithms that had been initially considered by NIST. Now there is an update of which ones were exactly are going to be standardized. So you see, if comparing to on top, you have the elliptic curve digital signature algorithm on RSA, which are what are kind of traditional ones that are used today a lot. And then you have these dilithium and Falcon. The dilithium is now called MLDSA. And if you look at the handshake times, you see that many of them are even faster than RSA. And the others are at least comparable to the digital signature algorithm that we are using today. So it doesn't look too bad, okay? Maybe as one drawback, so these ones below here, the Sphinx, they're now called SLH-DSA. These are the ones that are based on hash-based signatures. So many people liked to use them because we have studied hash functions since a long time. So we're quite confident that this works out well. It has the big drawback that indeed, in this case, it does take quite a bit longer for the handshake. On the other hand, so this is really just the TLS handshake. Maybe that the hash-based signatures take longer. It is not so surprising because if we look at key sizes and certificate sizes, they are extremely large for the signature size. So of course, all this has to be communicated. The other post-quantum algorithms also lead to a little bit larger key sizes than the ones that we are using today. However, not quite as much, okay? It seems here for the TLS, it's okay from the speed point of view, but depending on your exact application, this might be an issue or might not be an issue, right? If you use IoT devices, it might be different. Also, if you look at how fast the different steps in the signing and key generation process are, they're actually lots of the different algorithms are different in different locations, okay? So some of them are very fast for the key generation. Others are very fast to generate the signatures. And the third ones are fast to verify signatures, but might take a long time to generate signatures, okay? Now in TLS, again, it's of course the setup is quite clear what we want to do, but depending on your use case, you might opt for a different signature algorithm. So there is not one signature algorithm that will is clearly the best for everything, but it depends on the precise use case. And so, for example, in the context of TLS, there is even some suggestions that say maybe we should have different algorithms depending on where we are in the certificate chain. So, of course, if I am a CA, many people will need to check the signature that I made, but I might only have to do it once, and that would not be that important, right? So how long, if it takes longer there. So some people say maybe it's best to combine things in the chain. We don't really know yet what will in the end be the way that will be adopted, okay? Yes, so this is what we will now continue doing this project with Securosys. And that's our goal is to now look at really this TLS handshake with the algorithms that have been standardized, and also include the new proposed algorithms. So there is some new proposed algorithms, for example, called Mayo, which seem very fast and which base on different mathematical problems. So people are quite hopeful. Of course, we will have to see if they're not broken anytime soon. But so we want to include both the standardized ones and the new ones. And we also want to check of how it might behave if we combine different type of algorithms in the certificate chain, for example. Yes, so stay tuned. We will come out with some results, I guess, right, Marcel, soon? Yes. Yeah. So what is my take-home message for you? So I think actually the post-quantum algorithms will become part of standards independent from the actual development of the quantum computers, just because regulators are now picking up on it. So I think they will be relevant, these algorithms. It doesn't look so bad. From all our experiments, we see that there is solutions that are totally doable. They connect well. It doesn't seem to be a big issue. But depending on the precise use case that you have, you might want to select one thing or the other. Okay. Okay. Yeah, with this I end. And thanks to our team, which is working on this. And thanks to Securosys for the joint project, which we continue doing. It's nice. Mm-hmm.